Welcome to 12.6 on sublimation and fusion. We're going to mainly focus on fusion. I think this will be a pretty short section. It's very similar to the last one, but now we're focusing on the solid to liquid. I was actually, I learned something brand new the first time this semester. It's in the margin. We use the term fusion to go from solid to liquid. And at first, that doesn't sound right. From solid to liquid, it sounds like the molecules are actually sort of separating from each other, right? In a solid, nearest neighbors are constant. These molecules would be stuck together for as long as you can. But then when you go to the liquid phase, now they're moving all around. So actually, I think I've been using fusion in the reverse way. The reason they call fusion from solid to liquid because they imagined having a little test tube and some crystals and then watching it melt. And as soon as it melt macroscopically, it would turn, I don't know why I turn this up here. It would turn into one thing, one droplet of liquid. So they're watching crystals fuse into the liquid phase. I think it's a really poor piece of nomenclature, but that's how it came about. And you're learning it almost along with me right now. So solid to liquid, notice is this one's plus 6.02 kilojoules per mole for water. Again, every chemical would have a different enthalpy of fusion. It would happen at a different temperature for every chemical. And so we're noticing that it's always endothermic. You have to put energy in to turn a solid into a liquid. So from the chemical's perspective, they're absorbing heat. So it's always plus enthalpy value. It's always endothermic. And one thing that I don't believe I said in the last one is that if you were to reverse it, if you go from, let me give myself a little bit more room. If you go from the liquid to the solid phase, well, we know that's freezing. We'll just also call it the enthalpy of fusion. It's just the opposite process. The enthalpy of fusion now, it will be negative. That one will be exothermic. So if you want to freeze water, you have to remove 6 kilojoules of energy to get every 1 mole, every 18 grams of water to freeze. And then same thing down here. We put ice into our drinks to cool it down. Every time 18 grams of ice melts or fuses into the liquid phase, 6 kilojoules of energy have gone into just that process. It's almost like it's gone because the thermometer doesn't know where it went, but it got stored in the motion of the chemicals. So again, imagine that this is ice at 0 degrees. The thermometer's sitting there on the ice and it's saying, oh, yeah, it's at 0 degrees. But it's pulling in all of this heat from the surroundings. And now you come back a little sometime later, and now it's all liquid. It's still at 0. So the thermometer says, yeah, it's the same. And at first, we might look at it and say, yeah, it's got the same amount of energy. But liquids carry more energy in their motions. So again, we're sort of refining how we think about energy. At first, you might have said the only way for two things to have different energies is to be at different temperatures. Now we're saying, well, they could be at different temperatures. Water at 40 has more energy than water at 20, but they actually could be at the same temperature, but just in different states. Liquids are carrying more energy than solids. Gases are carrying more energy than liquids, even if they're at the same temperature. Another thing that you'll notice is that fusion took a lot less energy than vaporization. Vaporization was 40 something kilojoules. Fusion is only 6. So there's 6 times more energy to evaporate than it is to melt. So we'll do it in the opposite direction here. How much heat is absorbed when 36 grams of ice melts at 0 Celsius? Again, we've got the reaction right here. That's melting. At some point, you want to get pretty comfortable looking at a chemical reaction like this and say, well, the chemical is the same on both sides, and there's no second chemical. Oh, the state is different. Solid to liquid. Oh, solid to liquid. That's for water. Ice to liquid. That's melting. So you should be able to look at a reaction and know what process it's describing. And say, so we got these 36 grams of ice. Grams don't do us a whole lot of good in chemistry. We have to measure things on the scale in grams, but we want to think about things in terms of number. So we want to get out of grams into moles really quickly. So we get out of grams into moles. That's using the periodic table. Oxygen 16, each hydrogen is 1.008. So this is 18.016 grams. Now I got something in moles because the grams cancel. And now I can say, well, 6.02 kilojoules were absorbed every time 1 mole of ice melted. So 36 divided by 18.016 times 6.02. So this is exactly or pretty close to 2 moles. So it's going to be double that. So 12.03 with 2 sig figs, you would just call it 12 kilojoules of energy. One thing I want to say here is about the words. So absorbed means endothermic, means delta H is positive. Released, if heat was released, that we know that that means exothermic. We know that that means the delta H is negative. So what sign should I put right here? And I know everybody at home just said, well, we'll put plus. It says absorbed. You actually don't have to say plus. Absorbed implies endothermic. So let's say that I always go back to money to talk about heat. Let's say you get home from the grocery store and someone asks you, well, how much money did you spend at the grocery store? You don't say negative $40. When they say spend, you both are on the same page that you have less money than you did before. And the same thing is happening here. When it says how much heat is absorbed, to put plus in is a little bit redundant. It's definitely on the plus side, but the absorbed indicates the sign. So technically, I mean, it doesn't really, it's not wrong here. It comes up more when things say released. So if they say, how much money did you spend at the store? You can't say negative 40. Same thing here. How much heat was released? You can't really say negative 12 if it was the opposite, because the released implies that. And it's sort of like a double negative. How much money did you spend? Negative $12. Well, you've confused the situation. You spent negative dollars. You released negative energy. So you don't really need that. If it just says what is the heat change, then you should definitely include the sign. I don't usually try to trick on that scenario, but you will see some problems in the book where it might say released, but then it doesn't have a negative sign. And I don't want you to be confused by that. And then the last little thing that we'll say here is, again, we talked a little bit at the very beginning on sublimation. Sublimation for water happens solid to the gas phase. What would the change in enthalpy for sublimation be? 0 degrees. What do you think this might be? Well, it turns out since water goes from solid to usually a liquid and then a gas, we found that liquid and then a gas. We called this one the change in enthalpy of fusion, and we called this one the enthalpy change of vaporization, and we got values on those. It doesn't really matter how water goes from solid to a gas phase, if it goes through the liquid first or if it sublimes. One way or the other, the water went from being a solid to being a gas, and so the energy is the same. So the enthalpy of sublimation is actually equal to the enthalpy of fusion plus the enthalpy of vaporization. So we saw the fusion was 6. That's weird. They gave two different numbers here, 6.02 and 6.01. And then 40.7. So the enthalpy of sublimation is just the energy of fusion plus the energy of vaporization together. So that kind of finishes up the sublimation and fusion section in chapter 12. Hope you're feeling a little bit more comfortable writing chemical reactions or looking at chemical reactions and noticing what state change they're mentioning, if there is a state change. And then also using those enthalpy values to convert between energy and mass. And we did this in the previous section too. So we got mass. This is something that you could put on a scale. And over here, we've got energy. And it's not obvious that they're related, but that's what these standard enthalpies are. They're telling us how much energy for 1 mole of that chemical. So it's relating the two. And we can use that as a conversion factor. So no matter how much you have or how much energy you're going to end up using, you can relate it through this enthalpy of fusion. And those are very easy to look up for a lot of different chemicals. And we're going to put all this stuff together, warming chemicals and then melting them and then warming the liquid and then boiling them and then warming the gas to see how much energy it takes to go from a solid to a gas. And part of it is the melting and the boiling. That's coming up in 12.7.